Hello. Today I wanted to go over one of the add-on boxes for the 141T, the 8443A tracking generator and counter that adds additional features to the 8553 RF section. There's also an 8443B, which is just the tracking generator without the counter, but the counter adds certain extra functionality to the tracking generator and to the spectrum analyzer that I think is pretty valuable, so I would say the A version is the more desirable of the two, and I'll explain why later on in this video. In addition to the 8443, there were two other add-on boxes for the 141T. The 8444, which is a tracking generator meant for the 8554 RF section and goes up to 1.25 gigahertz. There's also the 8445 pre-selector, which is an 18 gigahertz pre-selecting tunable bandpass filter, which adds some functionality to the 8555 18 gigahertz RF section plug-in for the 141T. But the one I have here today only goes up to 110 megahertz. It adds certain extra cursor functionality to the 8553 that it doesn't have on its own. So you can see here I have it locked onto the 30 megahertz peak on my spectrum analyzer display here. You can see the cursor shows up as this slightly brighter spot, and if I move the marker, you can see the counter loses lock on the frequency, but if I move it over to the second peak, it locks onto the second harmonic and it shows 60 megahertz on the frequency counter. And you can also adjust the gate time of the counter to get more resolution. So you can set, so right now it's set to 1 kilohertz. You can also drop it to 100 hertz and even 10 hertz, but you can see that it actually will pause the sweep midway through and dwell on that peak for a little bit longer, so it makes the display flicker. Just something to keep in mind if you are using one of these. So it's not ideal for doing fast sweeps like this. The other mode that it has, so right now it's in restore signal, so that's what allows it to lock onto whatever peak the cursor is hovering over. Or you can set it to track analyzer, where it just sort of becomes a general cursor that shows you what frequency you're at on the plot. And this will be useful also for the tracking generator later. I'll demonstrate how to use that. But this doesn't require a signal to lock onto. It just sort of roughly tells you where on the sweep you are with that cursor. The frequency counter also has the ability to be used as an external frequency counter through this input here. You slide that over to external mode and it will just read the frequency through this input here. So what I've brought into frame on the left over there is a 10 megahertz rubidium reference. I'll bring this up later when we talk about calibrating the internal reference oscillator in this thing. But for now, we can just use it to demonstrate the external counter functionality of it, where you can see if I plug it in here, it shows 10 megahertz on the counter. So, in addition to being able to lock onto the frequencies of signals through the spectrum analyzer, it can also be used as a tracking generator. Now, what does a tracking generator mean? It means that this RF output here generates a signal that sweeps at the same frequency as the sweep of the inside of the RF section. So this can allow it to be used almost like a scalar network analyzer to characterize the frequency response of certain of devices, whether that be a filter or possibly an amplifier or what have you. So right now I just have it connected with just a cable, so you can see it's just a straight line across. The loss of this cable is going to be pretty low, down at 100 megahertz. Nothing too much to worry about. But what I have off to the side here is I just cobbled together a very quick and dirty bandpass filter to demonstrate this. So if we disconnect this cable here and connect our filter in line with our tracking generator and our spectrum analyzer, you can see now we have a bandpass filter. We now have the trace on screen is showing the frequency response of that bandpass filter. And if we go to marker mode, we can use the frequency counter to actually characterize this filter a little bit. So if we wanted to, say, measure the 3 dB bandwidth of this bandpass filter, if we just zoom in on it a bit. So if we say it has a passband loss of about 1 dB, so we'd say the left 3 dB passband would be about 18.5 megahertz, and the right would be about 28 megahertz. So it has a bandwidth of, let's say, about 9 to 10 megahertz. But something like this can be really useful if you don't have access to something like a full-on network analyzer. You can use this to turn a spectrum analyzer into something akin to a network analyzer and get some of that functionality. So this can be really useful, and also can be especially useful for things like the higher frequency 8444 tracking generator, which goes up to 1.25 gigahertz, as I mentioned. Now that we've demonstrated some of the functionality of the 8443, I wanted to talk a little bit about what it takes to get one of these working, because on the 8443 tracking generator and the 8445 pre-selector, there is a very big catch. And the catch comes in the form of this cable right here. In order for the add-on box to be able to know where along the sweep the spectrum analyzer is, it needs to be able to talk to the internal functions of the spectrum analyzer. And it does so by way of this cable. Now, the add-on boxes themselves are not difficult to find. If you were to look on eBay right now, there are several for sale. They're not especially rare. The problem you run into is that they almost never come with this cable. And the cable is rare. So because of this, you might end up spending as much, if not more, than you paid for the add-on box just to buy that cable. So in order to use the 8443, you need this aux-A cable for the back of the 141T here. In order to use the 8445, you need the aux-B cable. So the aux-A cable has the part number 08443-60009. It's what's called an 8W8 D-sub connector, so it has 8 coaxial positions. The part for the 8445 pre-selector is what's called, has the part number 08445-60007. It's what's called a 17W5. So it's 5 coax positions, 12 digital pins, so 17 pins total. And the 8444, interestingly enough, doesn't require an aux cable. So it's done all through 3 B and C cables on the front, which connect to the RF plug-in. So those are a lot easier to get up and running because they don't require an aux cable. Now, if you aren't able to source one of them, or you don't want to pay the full price like I did, you may need to build one yourself. And doing that is not as difficult as you might think. So you can order the parts for an 8W8 or a 17W5 through distribution like DigiKey or Mauser. You can tell from the green and black sleeving on this that this is not an OEM cable. I built this myself. It's a shell size 4 is what it's called, and I did a whole write-up on these on an electronics forum a number of years ago. I'll link to that in the description below. Another last thing to note is not all versions of the 141 are going to be compatible with these add-on boxes. So, namely the older versions, the 140A and the 140B, the 141A, the 141B, are not going to have these aux connections on the back. So they're not going to be compatible with the 8443 or the 8445, but they will be compatible with the 8444 because it only requires those front connections. Another thing to keep in mind, and this is pretty subtle, is that based on my reading of the manuals for these add-on boxes, not all spectrum analyzer plugins are going to be compatible with the add-on boxes. That certain serial numbers from about 1972 or prior may not be compatible out of the box with the tracking generator plugins. So you're going to need to read through the manual, check the serial numbers on your IF and RF plugins to make sure that it's within the serial number range that would have this feature by default, or some the manual did make reference to a retrofit kit for it, so it's possible even if you have one before the specified serial number range, it might have been retrofitted, but just something to keep in mind. So the last thing I wanted to touch on here was the subject of calibration. Now, I'm not going to do a full calibration video for this. I don't necessarily have all the equipment to do this or all the riser cards to get the various boards out of these shielded modules here. But I did want to quickly just talk about the power supply adjustments and also adjusting the reference oscillator for the counter, because those are two calibration procedures that are pretty straightforward and would be useful for the end user. So there are 5 voltages to check. There's going to be a 5.8 volts, 20 volts, 24 volts, 12 volts, and then also plus 175 volts down on the board there. The test point isn't visible, but I'll show that in a minute. So for the 5.8 volt rail, the printing on that plexiglass panel for some reason says 6 volts, but the manual says that the specification should be 5.8 volts plus or minus 0.12 volts. So if I touch the test point through the panel here, I'm measuring 5.802, so that's pretty much spot on. The 20 volt rail, I'm measuring 19.95 volts. The specification for that is plus or minus 0.4 volts, so that's not a particularly tight tolerance, so we're well within that. For the plus 24 volts, the tolerance is quite a bit tighter. They specify plus or minus 10 millivolts. So I'm technically out of spec on that. I'm measuring 23.96 volts. So if I wanted to adjust that, the adjustment potentiometer is right here. But if I'm being perfectly honest, the unit works just fine, so I'm not willing to mess with it because I'm not going to be doing all the other calibration steps afterwards. And if you adjust the power supply voltage, you're more likely than not going to detune the calibration of everything else after that. So I'm just going to skip that. I'm going to call that good. And next is the plus 12 volts. So I'm measuring, minus 12 volts, minus 12.24 volts. And the specification in the manual is minus 12 volts plus or minus 0.24 volts. So that's right on the edge. But again, there's no adjustment for it that I can find. And so I'm just going to call that good. The last one is plus 175 volts, plus or minus 3.5 volts. So if you, there's a test point down there. Here, I'll take the camera out of the tripod here. So if you look down on the board, that test point right there, you're going to have to reach down with your multimeter probe and check it like that. So if you touch that test point there, then I'm measuring 178.6. So again, the tolerance on that was plus or minus 3.5 volts, so I'm again a little bit out of spec on that, but the unit's working, so I'm honestly not too bothered about it, especially because I'm not going to be doing all the subsequent calibration steps. But if you have a unit that's not working, this would definitely be the absolute first place that I would look. So the last calibration procedure I wanted to go over was the calibration of the reference oscillator. So this right here is a 1 megahertz oven crystal oscillator, and that is what is used as the time base for the counter on the front here. You can see down here I have my rubidium reference, so both this unit and the rubidium reference have been running for several hours just to make sure they're warmed up and stabilized. The manual for the 8443 recommends that you leave the unit plugged in for 3 days continuously. I think that's a little bit overkill, but if you want to be really precise about it, that would be the amount of time to leave it on for. But I would say for all intents and purposes, an hour or two should be probably enough to get it warmed up. So the method we're going to use to calibrate is by measuring the beat frequency of the reference of the rubidium reference against the internal 1 megahertz reference on an oscilloscope. So if you look on the back of the 8443, there is a BNC connector that says 1 megahertz reference out. You're going to connect that to have it connected to channel 1 here, and the other channel you're going to connect to your reference. The manual recommends you use a 1 megahertz reference to measure the beat frequency against. All I have is a 10 megahertz reference, but we can still make that work. Notably, you're going to want to have the oscilloscope triggering off of the lower frequency of the two, so the 1 megahertz waveform here, because if you have it triggering on the 10 megahertz reference, it's going to be jumping all over the place because it might not be triggering off of the same cycle relative to this one. So you want to have it triggering off of the lower frequency of the two. Just thought I would mention that. So the adjustment point for the oven crystal oscillator is on those two plugs right there. So those screws on the one's partially obscured by the case, the other on the right are the coarse and fine adjustments for the crystal oscillator. And those screws are not the adjustments themselves. They're actually caps that need to be taken off before we can do the adjustment. So my unit is pretty well in cal, so I'm only going to do the fine adjustment, but obviously if yours was way out of cal, you'd probably want to also start with the coarse adjustment, which is this one, and then move to the fine, but I'm going to just remove the cap for this one. And it's a little bit fiddly here, because you kind of have to come in from an angle over the display unit, but just be patient and you'll get there. What I think I'm going to do actually is I'm going to grab a pair of tweezers so I can hold that screw as it comes out so it doesn't drop down under the board there. Okay, so now with a pair of tweezers in hand, I'm going to remove that screw the rest of the way and hopefully not drop it down into the case, but watch me probably mess it up anyway. And caught it. So you can see that this is just a screw with a little gasket on it, and the real adjustment is down inside of this guy here. I think you're supposed to use a non-conductive screwdriver, but unfortunately all I have is a regular screwdriver, so we're just going to have to make do. So it turns out I lied. First of all, I do have a non-conductive screwdriver. It's actually one of the little probe adjustment tools from a set of cheap oscilloscope probes. But the other thing I found out is that I think I do need to do the coarse adjustment on this crystal oscillator, so I'm going to remove the screw for that as well. Just hold it with the tweezers so that it doesn't drop down, and there we go. So that is the other cap off. And I think they are both the same length, but I would keep track of which is which just in case. And so now, if we look at our oscilloscope, we can see that when we adjust the crystal oscillator, it should change the beat frequency. I'm just going to very gently adjust this so you can see the beat frequency just slowed down a lot. So the goal here is to get the beat frequency to be as low as possible between our very precise 10 megahertz reference and our 1 megahertz reference. So the test they recommend is I think they said 5 seconds beat frequency, but because we're using a 10-to-1 ratio on our references, I think I'm just going to shoot for a half second beat frequency for one cycle on here to to up here. But I think I was able to get it such that they're basically not moving relative to each other, and I haven't even done the fine adjustment yet. So that should be good enough even as is. Yeah, I mean, I don't know what the beat frequency is exactly between those two, but that is well within 5 seconds or half a second per tenth of a cycle. So I'm going to call that good. Alright, and so just to close this unit back up, I'm going to take those 2 plug screws and put them back on the unit. So I'm going to start with the coarse one and then do the fine one, and really hope I don't drop them. Well, I dropped it. Yeah, I think you get the idea. So I'll be back when that's done. So that's everything closed back up on that unit. and our frequency counter seems to be working well. You might see it flicker between all zeros and a 1 on the end. That's pretty normal. Even when a frequency counter is perfectly adjusted, you're always going to have an error of plus or minus 1 count on the last digit. So that's normal, and I think that is perfectly good in terms of the calibration. Hopefully this has been a good overview on how these units work, how to set them up, and do some very basic adjustments on them. But hopefully that's been helpful. And if you have any questions, feel free to leave a comment below, and thank you very much.